Now, hopefully most of you have heard this song. Maybe your parents sang it's everybody wants somebody sometime. Everybody needs somebody now. Okay, that's actually written by a discrete math professor, I'm pretty sure, to illustrate the concepts of working with different qualifiers, for alls and there exists, and being able to say negations. So what we're going to do is we're going to take some of the lyrics of this song and talk about how do we state it in a purely mathematical sense. Now think about that for a moment. And I'm just going to keep it really simple. I'll use one of the lines. Everybody loves somebody. Now, we're not examining the truth of the statement. No, not at all. The statement may be true, it may be false. That's not even relevant. We want to know, how do you mathematically make a statement like this? And how's every way you can say it? And what about the negation of a state like this? In other words, if you don't believe this is true, what would the negation of the statement be? So what we want to do is break it down. But the thing is, it's not as simple as, oh, for all X, boom, because there's two things going on here. So I have two different sets. So we can break this down and we can say, let's let X be an element of the set of, let's just call it the set of people. And in this case, Y would also be an element of the set of people. And I'm going to be really loose because the set of people is really, really big, obviously, everybody on planet Earth. So X and Y will represent variables. So if I wanted to write this, everybody, how would I say that? That would be for all X. Now we can call the set of people, if you want, just, I don't know, let's big S for I like big S, the universal set. Okay, but we have to define, let big S be the set of all people. We have to say that somewhere in the problem. So for all X in the set of people, everybody loves somebody. For all X in the set of people, there exists a Y. Now, Y could come from a different set, but Y is a person, so Y probably should come from the set of people as well. So here's what we got. Everybody in the set of people, for every person in the set of people, there's a person also such that X loves Y. Now, that doesn't sound very mathematical. Love is, of course, not very mathematical. So what we can also do is create a function, and let's call it the L function. LXY would translate as X loves Y. LAB would translate as A loves B. Right? We can define a set in this way, and that's probably a cleaner way of doing it. So, and once again, you wouldn't just state this unless you defined what S and L actually are, but this makes sense. So what you didn't realize, this very popular song that was probably around when your parents were kids, or maybe your grandparents were kids, I don't know, was actually just basically a way of practicing mathematical statements. So everybody loves somebody. For all X and S, there exists a Y and S such that L of XY. Yeah, you didn't know it could be like that. So then the next thing is, how do you negate a statement like this? Now, this is the tricky thing. So I'm going to come back to the negation in a moment, because that's a little bit more complicated. Now, in general, when we're making these humongous statements, and basically we're saying we have two qualifiers here, okay? Because everybody and the somebody, there's two different things going on there. So if I have a situation where I've got two statements, okay, how do I state the statements? All right, so we're going to do it formally like we did last day. For all X in D, okay, now there exists a Y in, let's just call the next set. We were calling it D the other day. Y doesn't have to come from D. All right, so let's say Y is in, I don't know, well, let's see, we're already using P and Q. All right, Y and T, I haven't used T yet. For all X and D, there exists a Y and T. These could be the same set. They don't have to be the same set. for all people, there's a dog. I don't think the dogs would come from the set of people. For all people, there's a car. I don't think the cars come from the set of people. So just in general, in my everybody loves somebody, obviously we're talking people and people, so they clearly are the same set. But if I said everybody loves something, well, that wouldn't come from the set of people. That would come from the set of things. So such that now, when I have a statement like that, I'm saying for all this, and remember we called capital P was sort of our way we said our premise. For all this, boom, we have P of X, Y, whatever it is. For all X and D, there's this Y and T. I should say, sorry, such that P of X, Y. And I know it's a lot of symbols. That's element, that's such that. And by the way, it's perfectly correct to spell out the words such that. You wouldn't write the word element. That's too simple. Now, the other one, the one that involves the existential qualifier, there exists an X in D such that for all Y in T, P of X, Y. Now that's the other way I can say it, okay? Again, no, I want everyone to understand, where does the commas and the such that's go? Whenever we do a for all, we generally comma, after a there exists, it's generally the such that. And then here, you notice there exists such that for all comma, because otherwise from a grammatical standpoint, it really wouldn't make a lot of sense. So these are the two forms, and we introduced these more or less last time. These are the two forms that we want to do when we have the two different qualifiers going on at the same time. So the second part of the problem is, how do you negate them? So I'm going to just be lazy and say, that is a lazy way of saying I want the negation. I'm going to put a negation in front of the whole thing, but now I want the words. Oh boy, that's tricky. For all X and D, there's a Y and T. Now put words in there. Everybody loves somebody. What's the negation? Everybody loves somebody. Nobody loves anybody. No, that's the antonym. That's there's full, there's empty, and there's nothing in between. No, everybody loves somebody. The negation is, there's somebody out there who doesn't love somebody. So the negation of everybody is there's at least one. Remember, the negation of for all yes is there's at least one no. That's an easy way of thinking about it. So the negation of the first one would be there exists an X in D such that what? There exists an X in D such that the premise did not hold. So how do you say that? There's an X in D such that for all Y in T, not P of X, Y. Now, what you don't say is there's not a Y or there's not an X. No. This says for every single X, there's a Y so that my premise is true. Everybody loves somebody. That's it. That's never going to fail. There's at least one person out there who doesn't love somebody. In other words, everybody loves somebody. This is loving somebody. This is they don't love somebody. So it's not that you negate the X or the Y, you negate the premise. Now, that's the one thing that we sometimes have a hard time saying, that's where you're going to put the negative in terms of words. Now, the second one, there's at least one case that is true for everybody. What's the negation of that? There aren't any cases. The negation isn't all cases, it's true. No. If I said there's at least one person out there that's going to live forever, what's the negation? There's nobody that's going to live forever. Not everybody's going to live forever. There's nobody. Okay. So the negation of there's at least one such this is true is this is going to be not true for everybody. So otherwise you can't say there's not anybody that is ever, never true, and there's too many negatives. So this says there's at least one time where it's true for everybody. You say, nope, there's never a time where it's true for everybody. So it's always not true for everybody. So for this one, it's going to be for all X and D. How do you say there doesn't exist a Y and T? for all x in D, for all x in D, there exists a y in T such that, again, not P of xy. Okay, so that's how we say the negation in this case, because otherwise, again, it's always the premise that we negate. So let's go back to everybody loves somebody. How do we negate that? Now, I would like you guys to try this on your own just for a moment. And let's use the same language we did before. L of xy would be x loves y. Okay, let's do that. And we'll call S the set of people. So X and Y both come from the set of S. I'd like everyone to try this. See if you can write a negation of that statement using just this logic right here. And using the exact formal notation that we used to start the class. So again, what we did was we said for all X in S, there exists a Y in Y such that L of xy. That was what we said. That's the direct translation of this. You didn't realize you could translate songs into mathematical statements, but it probably makes it much easier to remember the lyrics, if you remember it symbolically like this. Or maybe that's just me, I don't know. All right, so the negation of this. Well, the negation of the for all would be something of this form. So let me go back here for a moment. I know this would be good. I just froze there for a second. Oh, that was weird. Make sure I'm plugged in here. Yeah, no, I am. Okay. So let me do this. Let me go back to the gallery. Does anybody think they've got this? If you do, I want you to just hold it up to the screen. That's the only way I'm going to be able to see it. If you've got it and you can hold it up to the screen for everyone to see. There's just not a lot of variations on this one. So hold on. Let me see if I can. Let me see if I can pin you. There we go. You're about half the screen now. Let's see if we can see what you got there. Oh, it's pretty light. I'm not sure if I can. It's the very bottom. Okay. The only thing instead of a comma, that would be a such that. From a language standpoint, but yes, that is correct. That is beautiful. So let me go ahead. Now there's the hardest part is coming back to where we were. And then pinning myself again. All right, let's try this again. And there we go. Oh, I don't know why it always does this. It does not allow me to pin. There we go. So Cynthia had this down. The negation of a for all is there exists an X. There's at least one person from the set of people such that for all Y's, there's at least one person such that if I look at everybody, this guy doesn't love any of these people. That's what we're actually saying. Such that for all boom, not. So in English, there's at least one person such that if we look at every other person, that person doesn't love any of those people. That's a very sad person, right? That they don't love anybody. But I love this example, by the way, because it's so easy to translate into the mathematics. So this is an example of the sort of stuff we want to be able to do in general. If something is stated in such a way that you can clearly see there's a universal or an existential qualifier in it, to be able to take the language, translate it to the mathematical symbols, because when you can do that, then writing a negation is rather easy. If you're trying to negate words only, sometimes the logic can escape us and we're not sure which part we're negating. Okay, remember the negation of for all is there's at least one that isn't. And the negation of there's at least one that is there are none that are. But that's probably the hardest one to actually say, is that there are none one. Okay, now I'm going to go back and I want to review a little bit of the language.
Professor?
Yes.
I'm sorry. How would you revert that back to I guess words, like the final negation?
Oh, there's at least one person that doesn't love anybody.
That's how we was just stated.
That's what if I was translating it back to English, everybody loves somebody, there's at least one person that doesn't love anyone. That's
Okay.
actually what that would be.
Oh, thank you.
Now, does that make sense though? That I guess the biggest thing is not even the symbols, or do you understand what actually constitutes a negation? So if you want, think of it in very mathy terms. You know, every real number has a reciprocal. Okay, that's a mathematical statement. It's not important whether it's true or false. That's a mathematical statement. Every real number has a reciprocal. For all x in the set of real numbers, there exists a y in the set of real numbers such that x times y equals 1. That's the same thing. How would I negate that? For all real numbers, there's at least one real number that doesn't have a reciprocal. Not no real numbers have a reciprocal. That's not the negation. The negation of for all is there's at least one that isn't. And by the way, that is a true statement. The negation is true. There's at least one real number that does not have reciprocal, 0. Oh, okay. So again, it's not important if the original statement is true or false. There is an absolute though. Remember, if a statement is true, its negation has to be false. And if a statement is false, its negation has to be true, because the negation isn't the antonym. You see, there's only 2 states this can be. It's full or it's not full. So if I said it's full and that's true, okay, then not full would be false. If I said it's full and that's false, then not full would be true. That's what I mean. A negation has to be the complement in that sense, logically.
Oh, I also have a quick question just
Sure.
before you erase it. Sorry, why is y in a different domain than x? Aren't they both just the set of people?
That's what we're talking about. This is the general. This is general. I said before, these could be the same. In the example that we just did, everybody loves somebody. Both x and y are coming from what? The set of people. What if I said everybody has a car? The everybody, x is coming from the set of people, but your y is coming from the set of cars. Does that make sense? Those are obviously different sets. In this example that we did, everybody loves somebody, both x and y are coming from the set of people. So in that case, we would use the same set, but it's just sort of a generic, this is coming from this set, this is coming from this set, and it is possible that these are the same sets, but it's certainly not required.
Got it. Okay, thank you.
Hopefully you got that. It can be, but it's not required. So it's safer to write these as different sets. So in the example I did, you wouldn't say for all x in S, that would be, for all x in the set of people, there's a y in a different set of people. No, the set of people is the set of people. That's really not the question. That example may have been overly simplified. Now, we talked about the terms. Hold on a second, this got any juice to it. Modus Ponens and Modus Tollens. These are really commonly used terms in discrete math, but they're not English terms they're not terms you've ever used in your entire life. And they're so simple that I don't want you to get bent. Oh God, modus ponens, I don't know what that means. Modus ponens basically means, oops, I'm starting with P implies Q, P, therefore Q. That's it. That's all modus ponens is. I have a conditional. I met my hypothesis, therefore conclusion. Okay. If we score more points, then we will win the game. We scored more points, therefore we won the game. That's modus ponens. That's it. If P then Q, P happened, therefore Q has to happen. Modus tollens is equally true, but modus tollens involves negations. And that's why people get it confused. P implies Q, not Q, therefore not P. If we score more points, then we win the game. We didn't win the game. Therefore, we didn't score more points. That's equally true. So we're saying these are both true things, but we're looked at, in a sense, that's the conditional, that's the contrapositive. That's it. But we're going to be using this because there's things like, universal instantiation of modus ponens. I mean, these are language terms. Like, what does that mean? No, it just means that there's a for all in there somewhere. So it's not something that I want anybody to struggle with. So there's something called a universal modus ponens that says Well, think of this in terms of the predicates, the premises, the P is involved, from a bigger set. So in other words, in this type of notation, so it would be something like this. If I said, let me see, I wrote down for myself. For all X, if P of X, P would be the condition that happened to X, then Q of X, that would be the conclusion that would happen to X. Okay, that again, these are very loose and generic terms, but you notice it's just an X, not a X comma Y in this case. So we're gonna fill in the blanks here. Let's see. Okay. So this is the statement that, anytime this is true, if this happens and this happens, you can think a mathematical statement. Okay. For all X in the real numbers, now make a statement involving real numbers, then Q of X would be a conclusion involving real numbers that is actually a true statement. That's really important. Could be something like this. For all X in the real numbers, if X is not equal to 0, then X squared is a positive number. That would be a really good one. Okay. So for all X in the real numbers, if X is not equal to 0, then X squared is positive. That's a true statement. We all believe that. This would be this one. This would be this one, because I'm starting with an X. This would be a universal modus ponens, because I'm doing a for all here. Okay, so I just want to make sure everybody understands that. So you're starting with that, but that's not the conclusion. Okay, so what I've got that statement there. Now just grab any particular outcome. Then we'd say P of A, where A is a specific, not an arbitrary, but a specific outcome. So we say P of A for some A. This is for every single X in D. This is for one particular, so A is in D also. A is just the value of X I'm using. In calculus, we would often do that. We'd say F of X, blah, 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 blah. Now, F of C, for a particular value of C, F of C, and then we'd make some conclusion. That's how we usually did things like continuity and differentiability. We'd say, if F of C is this, or if F prime of C is this. So P of A for some A, then my conclusion would be Q of A. Okay, so the example I just did, for all real numbers, if my X is not equal to 0, then X squared is greater than 0. So this would say, pick a value for A, 7. Okay, A is 7. So 7 squared is greater than 0 is still a true statement. 7 is not equal to 0, 7 squared. Pick any specific number, and then that would be my conclusion for that number. This is called universal. Okay, universal modus ponens. So then what would universal modus talens look like? Write this down. Universal modus ponens. I'm going to be lazy. All right, so what does universal modus talens look like? Well, same opening statement, but now it's the not this part. Okay, so it'd be the not this part would be, how do you say that? Not Q of A for some A, then not P of A. Oh, okay, because that looks like a contrapositive. Okay, so this is sort of the generic, and the reason I'm showing you this, there's nothing about this that's even all that interesting, because this is, I hate to say it, but this is the oh duh. I have a conditional. We believe the conditional is true, and you can make your conditional a for all if you want. Let's say you like eggs. So if you have breakfast today, then you're going to have eggs. So for all breakfasts that you eat, your conclusion is you're going to have eggs. If you didn't have eggs, then you didn't have breakfast. But that's kind of what we're saying here. But the idea is, because when we make blanket statements, all cheaters sit in the back, Larry sits in the back, therefore Larry's a cheater. that's coming exactly from this. But this is modus ponens, this is modus tollens. Is it possible for me to rearrange these two statements right here and make them not true? Yes, because this is think of this as a conditional. P of A implies Q of A. Think of this as a contrapositive. Not Q of A implies not P of A. We then have the converse and we have the inverse. Oh, so that's what I'm trying to get at here. What does a converse error and an inverse error look like? Okay. If a polygon is a square, then it is a rectangle. If a polygon is not a rectangle, then it is not a square. If a polygon is a rectangle, then it is a square. If a polygon is not a square, then it is not a rectangle. Well, those last two were incorrect. One was the converse, one was the inverse. But I'm using all of the same words. I'm just slightly rearranging the orders. Oh, so P implies Q, not Q implies not P, go hand in hand. Q implies P is the converse, not P implies not Q is the inverse. Now we know this. So what does a converse error look like? So let me write, again, with the same statement right there, the converse error, and we're going to do a whole bunch of these because they're kind of fun to practice, and an inverse error. A converse error would be Q of A, and I'll leave out that for some A, then P of A. The inverse error would be not P of A for some A, then Q of A. And what makes these particularly difficult in general is when you're using the exact same words and you just simply rearrange them, sometimes it's difficult to tell if you're saying the same thing. All cheaters sit in the back. Larry is a cheater. Larry sits in the back. I could have said, therefore, Larry sits in the back. That is a true statement. All cheaters sit in the back. Larry sits in the back. Therefore, Larry's a cheater. That's Converse error. That's what I'm getting at. That's where it can get kind of tricky. Okay. It's most of the time, this is a fairly simple thing. I want to go through a few of the problems. I'm just going to grab some out of the book because there's a whole bunch of them. I don't have to be clever. I gotta find them first. Hold on.
Excuse me, Professor. Is it not P then not Q, or not P then Q?
Oh, thank you. Yes, that's a not. Good catch. Because you guys know, when we're talking about the, Larry sits, back, blah, 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 blah. When we're doing that, so far, when you guys have been practicing, when something was invalid, it was probably a converse error because all you did was, it was the same words. And so the question I always get is, how do I know the difference between a converse error and an inverse error? Easy. Inverse error involves negations. That's the same as how do I know the difference between a conditional and a contrapositive? Easy. Contrapositive involves the negations. Oh, the inverse basically looks like a contrapositive just in the reverse order. A converse looks like a conditional just in the reverse order. It's the negations that give away that something's an inverse. But just because you see negations, no, it might be modus tollens. Okay, it might be totally okay. So I want to do a few of these guys. So the first thing I want to do is just do some translations. Then we want to write negations. So I'm going to grab some problems from the text. Again, because I don't feel, sometimes in the morning I don't feel that clever. So I'm looking at section 3.3. If you have a fifth edition, I'm looking at problems 13 on. So for all color C, there exists an animal A, and this other likes using such that A is colored C. All right. I would like to rewrite this. Now here's actually I would prefer to use a such that symbol, sorry, because it's very mathematical. This is a mathematical statement. So the first thing I want to do is translate this into words. Now, when you translate into words, you want to avoid saying for all and there exists, because that's the same. If I wrote for all, that's still symbolic notation. I just chose to spell it out in much the same way. If I said, I'm going to replace this with AYE, and I'm going to replace this with, SEE. I'm being silly. I'm going to spell out C. No, that's still C. That's not. Yeah, spelling it out is the same thing as using a symbol. So how do I say this in English? For all color C, there exists an animal A such that A is colored C. Anybody want to try that? Just yell it out. How do I say that in English? By the way, it doesn't matter if it's true. How do I say it? There's actually a really simple way to say that. There are animals of anybody?
Every color.
Every color. Yeah, that's it. Oh, okay. Not every animal is every color, but there are animals of every color. So for every color, there's an animal. You could say it like that too. For every color, there's an animal. Just avoid for every color there exists a unique animal A. No. That's mathy. So there's an animal of every color. Okay, great. Now, it may be easier to negate the English, believe it or not, than it is, because we want to negate the statement symbolically. So our goal is, and a lot of what we do in the first few weeks is all about translating. How do I make words into symbols? How do I make symbols into words? Because if I can do that, then writing things like negations and contrapositives and stuff become much, much simpler. To me, it's much easier to write the negation of a mathematical statement symbolically than it is with words sometimes. Okay, there are animals of every color. How do you negate that in words? Anybody want to try that one? There are no animals of any color. No.
Would you say there is an animal that is not, I don't know, blue or something like that?
Well, but that is that the negation? See, you're getting a particular color. How about if we keep it vague to say there's a color out there?
There's a color out there.
What?
There is a color there that no animal has.
Yep. Now, is that beautiful? Is that beautiful flowing poetic English? Probably not. But is it correct? Absolutely. So there's a color that no animal is. Now, I hate the way that sounds when I came out, but you get the intent. Oh, okay. So, right, we said for every color there's an animal, or we said that animals are of every color. There's a color out there where there's no animal of that color. Some version of that. Now, that might be easier to now do the negation. So I want everyone to do this. Yeah, I can do this for you all day long, but I want you to try to do this. And I'm not even going to ask you what you got. I just want to give you a head start. Give me the negation of the statement. And this statement here, the symbolic version of this statement. For all color C, there exists an animal A such that A is colored C. Now we want to negate that mathematically. And by the way, when we negate it mathematically, maybe that makes the English easier to translate. One of the things as math people, we absolutely have to be able to do. We have to be able to translate back and forth. I'm not worried about the negations. I'm just saying symbolic notation to English, English to symbolic notation. That has to be a skill that we are really good at some point, because otherwise we create ambiguity. All right. For all C's, well, we just said there is a color out there that, so the negation is going to be, I believe, there exists color C. Now what? Well, remember the such that generally follows the there exists. Such that, there is a color out there such that, how do we say no animals are that color?
Not for all, not a.
Yeah, but by the way, this actually is not a symbol that we would ever use in a mathematical.
No, I mean the not, which is.
So you're right. Yeah, you're right. Wait a minute. There's a color C says that. No, but I can't say no animal when I have for all. So I'd say such that for all A, what? There's no animal colored C. That means all animals are not C. For all A is not C. Okay, so we don't say not for all, we say for all. Remember, we said not conclusion. The conclusion here was that something was colored C. That was the conclusion. So here is, it's not colored C. You could say A is not colored C in words. You could do that too. A is not color C. For every animal, that animal is not this color. There's a color out there that every animal is not that color. Okay. That again, the English is, maybe not tremendous, but we've got the intent. So this is just, again, there's nothing, it's not important if the statement's true or false. It's important that we can translate it. And that's one of the beautiful things. It's not important if a statement is true or false, because if I can translate it, it actually makes it easier to interpret whether it's true or false. Because if I don't believe it's true, and I translate it correctly and I don't believe it's true, then I can find a counterexample. But if I don't translate it correctly, then it may be true and I've mistranslated, or maybe false and I've mistranslated. Both are bad. All right. I like the next one too.
Professor.
Yes.
So is there a reason why we didn't include like for all animals A instead of for all A? Or for A,
yeah, for all animals A.
is the same thing, or is there an actual?
You know what? Let's throw that in there if you want. For all animals A, because we're saying A represents an animal. So for all A in the set of animals, for all animals A, you're kind of saying the same thing. A perfect example, by the way, I'm glad you said that. Perfect example. I might make a statement about real numbers. For all X in the set of real numbers, blah, 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 blah. There exists an X such a blah, 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 blah. Sometimes we would leave out there exists an X that's still in the set of real numbers because we've already defined X as being in the set of real numbers. But you're right. It's absolutely correct to say for all animals A, but we said A represents anything in the set of animals. You could look at it as being redundant, but it's probably safer. It doesn't hurt anything to do that. All right. So there exists a book B, B is the book, such that for all persons P has read B. Now, that's the way it says in the textbook, but I'm going to change that last piece because I want it to be more mathy. So let's say RPB means that person P read book B, okay? So if insert your name here, insert a book you read, okay? So I'm going to change this for all persons P. RPB. P has read book B. That's what this means right here. I'm going to use that language instead because I think from a mathematical standpoint, it might be easier to write. So it says, there exists a book B such that for all persons P has read B. Anybody want to translate that?
There is a book that everyone read.
Yeah, that was awesome. There's a book that everyone's read. Again, does it matter if it's true or false? No, that's the translation. There is a book that everyone has read. Okay, in fact, I might want to write that down. There exists, there is a book that everyone has read. And there's no symbols in that. And that's an exact perfect translation of what we just said. Now, maybe it's easier to translate the words. Again, I don't know if it's easier to translate the words. We want to do both, but let's negate. I'm sorry, I shouldn't say it. it may be easier to negate the words. Sorry. So let's see if we can negate the words there. Anybody want to try that one? There's a book that everyone's read. I don't think that's
There
true.
is a book that someone has not read.
Well, but is that a negation? But if I just said, hey, there's a book out there and everybody's read it, okay? Could, you know, my autobiography has been recently published, and I just checked, and everybody's read my book. Okay, there's a book out there and everybody's read it. So I think the negation, don't refer to a specific book. Oh no, not everybody's read this book. Yeah, but we didn't say that book. We just said there is a book out there. So first of all, the negation would be, how about there isn't? So in words, let's keep it simple in words. There's a book that everyone has read. Keep it simple. How do you say there isn't?
There is no book that everyone has read.
There is no book that everyone has read. There is no book that everyone has read. But remember, we're going with the English. This is not the formal mathematics. Would it be correct to say there isn't? There is not a book that everyone has read. Yeah, it's the same thing. Now, you can't mathematically say there exists not book. You know, that. Okay, so there is no book that everyone has read. There is no book that everyone has read. How do you say that? Well, remember the negata there exists with a for all. So how about for all books be there's a book that no one has read. Or let's see, there is a book that everyone has read. Hold on a second. There is a book, oh, actually, you know what? Actually, there's another one. There is a book that everyone has read. There isn't a book there. This one's actually a little bit trickier than I thought. This is kind of cool. There is a book that there is no book that everybody has read. Now, by the way, there's a book that everyone has read. Okay, there exists a book such that all persons has read the book. There is a book that nobody has read. Well, that's actually still possible, even with this statement being true. There's a book that no one's read. There's nothing wrong with that. That's not the negation of this, because that could be true. In fact, we're saying there's a book that everyone's read. There may be lots of books that nobody's read. So that's not a negation. We don't believe there's a book that's been read by all people. We don't believe there's a book that's been read by all people. So how do we say that? So that I want everyone to try this one. Again, try it on your own for a moment. And if you think you know it, just say it out loud. I don't, it takes forever to do the screen changing. How would you say that one out loud? Now, just again, remember you're negating a for all and a there exists. So how you say it is actually really, really important, because it's not automatic. You can't just reverse the words.
Is it for all B, for all P, not R?
For all P. Well, no, you're in there. You're almost there, because we're saying we're going to do a not that thing at some point. So how do you say it formally? It's for all books. There's a book that there's no book that everyone has read. So how do you say that? I'll kind of guide you. There's a book There's no book that everyone has read. So every book out there, for every book that exists, there's somebody that didn't read that book. Does that make sense? There's at least one book out there and everybody's read it. Okay, now we're saying, I don't believe that's true. So I think for every book that exists, you're always going to find somebody who didn't read that book. And if that statement is true, that means there's a book out there. There's no such thing as a book that everyone has read. So for all books B, it's not there's a book, it's there's a person. For every book B, there exists person P such that you're on the right track. Such that what? If you got nothing else, aren't we always negating the conclusion? Such that not for every book that exists, there is a person who didn't read that book. Remember, this would be not, so they didn't read that book. Person P did not read the book. Now, this one was a little bit trickier because it's the nothing. Sometimes it's easier to negate the for all than it is that there exists, I think. So for every book, there's a person that didn't read that book. So that means every book on planet Earth could have been read by every person on planet Earth, but each book had one person that didn't read it. That's one way of thinking about that. So let me, right. There's a couple more problems I wanted to, oh, there's another one. I wrote down which ones I wanted to look at. Okay, so another nice little exercise I like here, again, is the words to symbols translation, and I want it to be really simple. And some of these I put on the quizzes almost verbatim. Okay, so I want to use problem number, it's problem number 11. Okay, let me keep this simple. Okay, so let W be the set of workers at, let's say, at your job. Okay, and let R be the set of restaurants in town. Okay, so I have two different things. I have the set of all workers at your job and the set of all restaurants in town. And we're going to say E small w small r is going to represent worker W ate at restaurant R. So in other words, little w comes from, big W, and little r comes from big R. So big R is the set of all restaurants, little r would be the individual restaurant. Big W is the set of all workers at your job, little w would be an individual worker. So if I say EWR, that means that particular worker ate at that particular restaurant. E for eat, that's try to make it easier on you. So here's what I want to do. I want to now translate words to symbols and or symbols to words. So how would we say every worker at the job has eaten at least one restaurant in town. Oops, in town. Okay, that's the first one I want to translate. Every worker at the job has eaten at least one restaurant in town. And the second one, let's see. Second one Okay. The second one I want to translate into words. So the first one, we want to translate the words into symbols. The second one, I want to translate the symbols into words using this. So take a moment. And again, I want you guys to always try these on your own before I go through the answers. You'll get more out of it that way. Every worker at the job has eaten at least one restaurant. Okay, every worker. I think we all agreed that would be for all W and W. All right, anybody want to finish that one off for me? Every worker, for all workers at your workplace.
There is at least one worker that hasn't eaten anywhere, right?
Well, you're doing a negation. I just want to translate this. This is not a negation one. Yeah, this is, I just want to translate this into symbols. Every worker, so for all W and W, there exists
R
At
element
least
of
one
R,
R.
R in the big set of R,
such that what is it called? EWR.
perfect. Everybody got that? That's perfect. For all W and W, every worker, there's a restaurant that person has eaten at. Every worker has eaten at least one restaurant. So for every worker, there's a restaurant that they ate at. That's what that exact translation. Now, the second one sounds like it's almost the same thing, but it's not exactly. It's not exactly the same thing. This says, for all R and R, there exists W and W such that, So how do you say that one in words? Ooh, for all R and R.
Every restaurant in town.
By the way, use whatever words make the most sense to you from a grammatical standpoint. Every restaurant in town.
How do you say it?
I like things like has been frequented by. How's that? Some version of that has been descended upon.
Has been frequented by a worker in the job site, or
Has been. What do you want to say? Has been. Because you don't say every restaurant has been eaten at. Could you say it like that?
visited, or yeah.
That just doesn't sound very graceful. Has been eaten at. I don't know even know if that's good English. By what?
A worker. What's it called?
A?
What is it?
Careful. We don't want to say every worker. We don't want to
By
say
at least one worker.
Oh, at least one worker of your
At
job.
least one, or could you say by some worker? Someone at work went to that restaurant. Am I saying at least one person went then? If I said, well, somebody I work with went to the restaurant. It could be 25 people I work with went, but somebody went. I know somebody went. So I know, I'm not saying exactly one person went, I'm saying somebody went. So that would be okay if you said it like that. If you said at least one, that's also okay. Perfect, that's perfect. But we want to make sure that, okay, that every there exists, every there exists. So we want to make sure we're always translating that part correctly. All right, now I want to move on to the next piece, which is a little bit different now. Okay, hold on a second. The next one, we want to do a little bit of practicing of the whole cheaters sit in the back kind of logic. I love those types of things because I find people make these mistakes all the time. And I've been watching, even a sporting event or something, and people will make statements, in a conditional form, and if then, and they clearly are saying it backwards, and you're saying, no, that's not correct. One of my favorite is, I'm a big football fan, and I don't know if you guys pay attention to football, but when you get near the end of the season, and they start talking about things that are called playoff scenarios. So your team, in order to make the playoffs, they might have to win the rest of their games and then have team A lose and team B lose, or team C tie with team D. They have all these infinite scenarios. And I'll be watching those going, no, that's not possible. You just contradicted yourself. And usually when they go through them, they usually make some error in telling you, because you're saying, no, you're saying this has to happen, but if this happens, then that other thing can't happen because you've contradicted yourself. You can't have these outcomes because they're reading from a piece of paper and they're not thinking logically. Team A cannot lose to team B and simultaneously beat team B, and things like that. So when we're doing these types of problems, I've got a whole bunch of them written down here. We want to be able to really, really simply analyze them. All right. Let's start with, oops, healthy people. Healthy people, not Heffley. Healthy people get plenty of sleep. Again, it's not important if it's true or false. Okay. Okay, go ahead and mute yourself. Okay. Biff gets plenty of sleep. Therefore, Biff is healthy. Now that everything about that makes perfect sense. Healthy people get plenty of sleep. So if I'm saying if you know anybody who's healthy, then you know they get plenty of sleep. It's not important if it's true or not. Healthy people get plenty of sleep. Biff gets plenty of sleep. Therefore, Biff is healthy. I think all of us would make that conclusion. Yeah, I watched Biff. Biff gets lots of sleep. That's all Biff does. He just sleeps 16 hours a day. Biff's healthy. Is that a true conclusion? Is this a universal modus ponens, or is this an error? Anybody want to chime in on that one?
It's an error.
Which kind of error is it?
Converse.
Absolutely. But it makes perfect sense. Healthy people get plenty of sleep, but can unhealthy people also get plenty of sleep? Sure, I didn't exclude them. Oh, so Biff could actually be in the group of unhealthy people and it still be true. Now, is it possible that Biff is healthy? Absolutely. All squares are rectangles. All rectangles are squares is not a true statement, but aren't there a lot of rectangles that are squares? Yeah, but not all of them. So how do I make this true? This, by the way, this is always how you make it true.
Switch the order of those two statements.
Yeah, only those two, by the way. And this, I love this type of exercise because there's nothing complicated about it, but it will really sharpen, I don't want to say sharpen your wit, but it'll sharpen your understanding of how to do this kind of thing. Hold on a second. God, my light is not great sometimes. Where's the one I want?
Professor,
Yes.
is this a converse error?
This is called a converse error because if A then B and I just said B then A, healthy people get plenty of sleep. How can I make, oh, by the way, I'm glad you asked this question. This is an easy way to translate this. Can you make this into a conditional? If healthy, then get plenty of sleep. If get plenty of sleep, then healthy is the converse. Does that make sense? Biff gets plenty of sleep, therefore healthy. That would be the converse because I just switched them. Oh, so I could make the first one into an if then. All right. This one is the best one. This is my favorite one. This one I even like putting on exams. No good deed. No, dead. No good deed. You all know this one. Goes unpunished. Sorry, punished. No good deed goes unpunished. Skippy does good deeds. I don't know why I see deads. Skippy does good deeds. Skippy is punished. No good deed goes unpunished. Skippy does good deeds. Skippy is punished. Now, this one's gonna take you a little longer. It's either true, and by the way, what would it be true by? But if it is true, my original statement sounds negate. It sounds like negations, but no, my original statement, the negations are the P and Q, if you will.
If it were true, wouldn't it be modus tollens?
It would, if it were true, it'd be modus tollens, and if it were false, it would be
Inverse error.
inverse error, because, but that's not a negation. No, but it's the negation of these. Could I start a statement with, if I don't get up today, then I will get fired? Can I start a statement that way? If P would be, I don't get up. And even though that's a negative statement, so the negation of P was, I get up. There's nothing wrong with that. Okay, so no good deed goes unpunished. If good deed, then punished. Does everybody see that's a correct interpretation? If good deed, then punished. If unpunished, then no good deed. So this would be if unpunished, then no good deed. And that's the same as if good deed, then punished. Skippy, good deed. Skippy, punished. True or false by inverse error? Those are my choices. True by universal modus tollens or false by inverse error. I didn't make this one easy on you because the negations are always harder.
Is it not modus ponens?
Well, but let's say it like this. Okay. Can you make this into an if then? No
If-
good deed goes unpunished. So good deeds require punishment. So if you're not punished, then you committed no good deed. So if not punished, how's this? Because I want it to match the wording, then no good deed performed. I can't think of a better way to say that. If you were going unpunished, then you did no good deed. Because what's the contrapositive? If you did a good deed, then you got punished. So if not punished, then no good deed. Skippy does no good deeds. So this would be technically, this would be my P implies Q. Skippy does a good deed is not Q. Skippy is punished. That's not P. So this is true by modus tollens. That I said this was a little bit harder. The negations are always harder. So how do I make this an inverse error? Again, if I had switched those, it would have been inverse error. Oh my goodness. No good deed goes unpunished. Skippy is punished. Skippy does no good deeds, or Skippy does good deeds. But that's the Larry sits in the back argument again. Now this one here to me is probably the hardest one, but setting it up as a conditional statement and in the negation form, by the way, makes it easier, I think, to interpret. Okay, let's do another one. We'll do another one in this one. I'll take from the book. So sorry. No. No good car is cheap. Okay. In fact, we might even believe that. I like to say a Simburu. They don't want to get sued, so they make up a name. So it's not Subaru. A Simburu is not cheap. Therefore, a Simburu is a good car. Oh boy. Well, that's kind of like the no good deeds, isn't it? kind of has the same vibe. So let's figure this one out. No good car is cheap. Now, I want to make that into a conditional statement, and I would really prefer it to have the no in the right place. So is it if not good, then cheap? Or is it if cheap, then not good? That's really important because those are not the same statement. No good car is cheap. So if the car is good, then it is not cheap. I think we agree with that one. If no good car is cheap, then if good, then cheap. So if, oops, sorry, let's try it again. If good, then not cheap. I think we agree that that is a correct interpretation, but I've got the negatives in the wrong place. So now let me take the contrapositive of this statement. If cheap, then not good car. Oh, no good car is cheap. If it is cheap, then it is not a good car. Good. I'm keeping the negation in the right place. So this statement here translates exactly as this statement here. If cheap, then not good. Does that mean if not cheap, then good? If good, then not cheap. No good car is cheap. Think of that, if it helps, think that means good cars are expensive. But doesn't that leave room for some expensive bad cars? If a car is, this says if a car is cheap, then it is bad. But if a car is bad, it is not necessarily cheap. That would be the converse of that statement. Okay, so if cheap, then not good. If not good, then cheap. Careful. So how about if not cheap, then good? That would be the inverse of this. If not cheap, then good. Not cheap, then good. This is inverse error. Okay? Not cheap, good. Hopefully you all see that. Like I said, this is the harder of the bunch to justify sometimes. I don't think this is trivial, but again, I think it's kind of fun. Anyway, I think that's enough practice. In the textbook, there are so many good problems to practice. And I have to keep emphasizing this over and over again. It does not matter if the statement itself is actually true. That's why I said we could be using gibberish, but we make a statement and then we want to pick it apart and analyze it. And we want to do negations and all these things so that if we are actually doing a mathematical process or I'm actually doing a mathematical proof, how do I know if my proof is completely valid? And that's really one of the big issues here is the validity of what I'm saying based on this type of logic. So we will go ahead and stop now.